Good afternoon, everyone. It is our pleasure to present a topic, a tutorial on making ICE research more reliable and valid. Perspective from the statistical power of the NHST and the power analysis in the SEM. This is the Shiau and my partner, Professor Guo. We are from the School of the Management, the ZJUT. Okay, let's outline. I will talk about the motivation and the problem in our ICE field. And also, I will share my teaching experience in the power analysis. And moreover, the reliable and valid SEM for the power analysis. And then the final one, we will talk about the power analysis for the SEM. The problem and the motivations. About 30 years ago, the Faraday and Oskid, they talk about the statistical power is the probability that a statistical test will correctly reject a null hypothesis. In their paper, they assume that a small, medium, and a large effect that handle sorry, there's a little interrupt.
Sorry, that was me by mistake. I put on transcript and I made you the host.
They had 99%, 69%, 34% under the 0.8 level power analysis. That's the 30 years ago. After nearly 30 years, the Meta ETL, they published a paper and mentioned about there are 83.7% paper didn't discuss the statistical power during the study design. 4.7% report post hoc power analysis. 9.3% study reportedly used the power analysis for the sampling. In what the AI's the senior scholar basket of the IS journal. That's the good journal in our leading journals. So what's the problem and my motivations? There's a neglected area in the power analysis. And before I present our contents, let me share my experience. And first, that I always like to introduce myself. You will see the 4 pictures over there. I have only one child. We feel the time fly like arrows. For what? That you can see lots of the books I publish. And my child grow up and we are getting old. So now I'm in the post-academic A period. What this means, we try to make our IS community better. So I did so many surveys on the journal and published many papers over there. And also it's my pleasure that I've been included in the list of the top 2 scientists in the world in the 2019 and the 2020s. And in the past 5 years, I published one high side article every year. So you may refer to these articles. And my research trend covered 4. The first one is core knowledge. The second is the SEM. The third one is multiple method. The fourth is the mixed methods. Most of the researchers know me about the SEMs, but I did many the core knowledge in our IS research. And you will see it. I will save time, so I will not get into it too much. And that's the books related to today's topic. I published many multivariate data analysis. So I noticed so many things over there. And the 2 books That's very popular right now and recommended by the T.P. Liang. Right now can only memorize him, the WKK and Page Chow. So let's go to today's topic here. The motivation I said a lot, and now I will get into our experience. So that's the problem over there. Last year, I go back to check and trace the critical power analysis research. You can see it from the 1928 to the 2020s. So there's so many history over there. The Neumann and the Pearson, the Fisher, and so on. And we start getting to more detail about 1989, the Faraday and the Orlowski, that's our ice field, and to the method and the records. And another one that's very famous, that's the Cohen. If you study the power analysis, don't forget to read the books and the papers from the Cohen. So I also get into the ice field to find out what happens over there. 30 years ago, you will find the Faraday and the Orlowski that find even though we assume the small effect or medium effect or large effect, then we have the problem for what? Nearly 99% they are below the power analysis, the needed level, 0.8. The median, that's about 66%. And the large effect, they still have the 34% below 0.8. So in our field, you can look at the table 6. We are better than a few disciplines and lack and not as good as other disciplines. So that's the 30 years ago. And now we still have the problem over there. We overlook or neglect the power analysis. So I go back to my teaching experience to find what the problem over there. The left one is the basic business static. I use it as a textbook. The right one is the multivariate data analysis. You will see the power analysis is mentioned in the field page over there. And what we teach is about the type 1 or type 2 error here. The reality is over there. And we use the statistical decision to teach the business how to make the decision here. If the reality, the null hypothesis is true, we reject it. We call it type 1 errors. And the alternative, if the alternative is true and we reject it, then we said it's the type 2 errors. What's the power statistic? The power analysis is about 1 minus the beta. Here you will see it in the right one. That's the easy way to understand, to make a decision. But what about, we set the alpha, we tested it, but we didn't mention or we didn't show the power analysis. These are our teachings in the business static and in the multivariate data analysis. So the problem is the master student or PhD students, even though the junior faculties, they know field about the power analysis. So even though you see the picture here, as we decrease the alpha, we wish to see more screen there. As the alpha decrease, the beta increase. The 1 minus beta, that's the power analysis, also decrease. So that's the problem here. We only can make the balance over there, but it's easy. The answer is the no. So what's the power analysis? There are 5 types of power analysis and the 4 parameters. The criterion, the compromised post hoc, priori sensitivities. The 4 parameters include alpha, 1 minus beta, the sample size, the population effect size. The 4 parameters, if you set 3 parameters or we set a fix, then you can get another one. For examples, if we set the alpha, sample size, and effect size, then we can get the power statistics here, 1 minus betas. So you can refer to the Cohen 1992 papers over there. So I'll give you another example here. The important thing is about the effect size. And in the papers of Cohen 1992, there are 4 independent variables in the regression. We set the alpha 0.05 and the power 0.8. The samples what we need, the small effect, the 0.02, we need the 599. The median effect, 0.15, we need an 84. The large effect, 0.35, we only needed 38 samples. And from this, you will see that the samples N affect a lot. So they were said then if our samples N is large enough, then we don't care about the power analysis. It sounds great and it looks correct, but we forget the effect size. If the effect size is very low, then your power analysis will also low. So then before we get into the power analysis in SEMs, then let me explain a little bit about the SEM, the reliable and the validity. Then we can get into the last mile about the reliable and the valid SEM. That's the power analysis in SEM. So let's go back to see the SEM. I cover a little bit about the evolution trend, correct report, and the common errors. The final part was lifted to the Professor Guo. She will introduce a little bit of detail. That's the whole picture of the evolution about the SEMs. The left part, that's early, from the 1990s to the 1980s. That's the very, very best ones. From the 1960s to the 1990s or the 2000s, we have seen so many analysis technique over there, like the bootstrap, like the linears, like the FASEM, and so on. And in the contemporary SEM, sometimes we saw the modern SEMs that from the 2000 to the 2020s. Also now, we will see the PLS, the multi-levels mixture, the meta, AMA, AMM, and so on. That's the whole pictures. So I always hear they say that the SEM, only the measurement model, structural model. Yes, they use the 2 stages to analyze, but the topic and the content is so large. Don't just say the measurement or structures. And let's see a little bit about the trend. I also hear that the SEM is not popular now, and the answer is no. I get into the ISI database and search from the 1985 to the 2020s. You will see that there's 70,399 papers they also increase every year. So SEM is still popular, not only in the IS field, but also in the other field. And two slides, I just want to show you that's my papers. We cover the various topics over there. Of course, I already did more than 20 years. So how to correctly report these papers or this type of research, you can see it. And that SEM, there are the two mainstream. One is the CBS SEM, we use more than 20 years. Another one is pillar SEM, it is a later one. The two complement each other, but sometimes we see the research mix. If you want to mix it, you must have the reasons. So as a AESE and the reviewers, I see so many research papers. They use the CFA, use the CBSEM, and the structural model and the modulation, they use the PLSEM. They don't give us the reasons. There's some problems over there. So the two mainstream, if you want to mix it, you can refer to my papers. I will show them some of my experience here about the two mainstream, the mediator and the modulators and the common errors there. The first one, they will mix the two methods, the CBSEM and the PLSEM. And I published it with Professor Chiao. If your model is very, very large, it is not too easy to converge. So I mean that it is hard to use the CBSEM approach. And of course, your model is a smaller one, and it is linear. So there's no reason you must use the Korean-based SEM because of what? It is get you more correct parameters. So you can refer to the topic here. The second one is about the mediation effect. And in the past, we always use the pattern canning and the sober test. And in the 2010s, the professors published papers. Now we has been into a new paradigms. In the past, we have the 3 types of the mediation. Now we have the 5 types. And for the correct ones, then the sober test has a problem because of what? It is limited by the normal distributions. So if the indirect effect is not normal distributions, we must use the bootstrap to test it. And another one, the critical issue, also the common error is, even though we see the many papers that use the Professor Zhao 2010 paper to do it, but they didn't explain the theoretical contributions. That's the last part in the figure. So if you want to test the mediators, don't forget to explain the theoretical contributions over there. The third one is the modulating effect. We said is the ratio types. Then it's better to explain the slope. I show you the modulating effect. And what we see more is the peoples that are use the divided the ratio type into the nominal type, the 2 groups. And if you use it, then you will lose the power statistics over there. So that's another problem over there. If you have the nominal types and you want to report the modulation effect, you will compare the path coefficient of the 2 models. So many the researchers, they cannot distinguish about the group comparisons. Of course, you can use the multi-group analyze method to do it. But don't forget, it is not the model comparisons. So sometimes I also see the research use the nominal type of the modulators, put them into the model. Then how could you explain the value of the 0 or 1, or sometimes the 1 or 2? How could you make sure they have the modulating effect? And the fifth one is the reflective, the formative types. The reflective and the formative model, the second, in a hierarchical model, especially for the second orders, we also see the many wrong result over there. The reflective and the formative second order, we have the 4 types. We call the R, F, FR, and FF. So that's the difference. If you have the formative the ones, then it's better to use the 2-stage and analyze, not use the reflective, the reflect type to do all the second orders. Of course, in these ones, there's so many the problematic research over there. The final one is about the correctly report the power analysis. I introduced a little bit earlier. And how about the common errors? The first one is we neglect the power analysis over there. The second one is if you have the effect size small, some researchers they may know or may not know, they don't report it. So how could you make sure you have the reliable and the valid results? So we give examples. Of course, we learn it from the Cohen and so on, so the books and the papers. The power analysis, then if you specify the effect size and the required the power level and the screening levels, then you can get the number, and that we call the samples, at least. The second part, if you need the post hoc analyze, then you can analyze and put the effect size, the screening levels, sample size there. Such in our papers published in the JGIMs, we have the completely the Chinese American data and separate, and we run the post hoc analyze. Then we'll get the statistical power 0.99, 0.998, and 0.939 respectively. And also, we could analyze it to do the test coefficients, the test. The most of the test coefficients are above the 0.8 in our papers. Then we can cross the target the power level of the 0.8. Then we can claim the statistical power is not a critical issue in the research. So there's so many things we need to report about the power analysis over there. And the more the power analysis, I've left it to the Professor Guo. The Professor Guo should introduce a little bit more. And at least you must know the power analysis for the SEM, the 2 research stream. And for the PLS-SEM, we have the statistical power of the pair analysis. For the CBS-SEM, we have to know more the model fit chi-square MSCA, the statistical power of the CFA, and the statistical power for the pair analysis. Okay. Let's welcome the Professor Guo to introduce the next part. Let me start my sharing under Professor Guo.
Oh, okay. Can you see my screen?
Yes, please.
Oh, okay. So thanks all for attending this workshop. I'm Shiau Guo from Zhejiang University of Technology. My current research interest is statistics in management. My part today is poll analysis for SEM, and it will include the following 4 sections. The p-value problem in big data, poll function, poll analysis for PLS, and CBS-EM. So we first start with the p-value problem in big data. Okay, let's look at the background. As we all know, hypothesis testing is a widely used method in AI research. However, it has been pointed out that the p-value in hypothesis testing is commonly misused and misinterpreted. Despite we all know that p-value is a very useful statistical measure. And nowadays, researchers can obtain very large amounts of data. We always say a big data. The big data brings new challenges to p-values since it can give support to statistically significant results, which may not be practically significant. So that's the background. And this slide is one comment published in Nature in 2019. And the title is Scientists Rise Up Against Statistical Significance. They mention the dichotomization of p-value and indicate that the researchers should learn to embrace uncertainty. And to address these issues, there is a special issue in the journal, The American Statistician, to lecture the researchers about what to do and what not to do with the p-values. And this special issue also offers 6 p-value principles to get the use of p-value. Actually, no matter Nature or the American Statistician, they are not advocating a ban on p-value, but urges the researchers to treat p-values more accurately. Then we look at some seemingly weird results in as top-tier journals. We can say that this value, actually, the estimate of this parameter is quite small. But it is very statistically significant. It with 3 stars. 3 stars means that the p-value is quite small. It indicates that it is a statistically significant result. And then we can look at the same things happen in the next 2 figures. Similarly, we have close to 0 estimates, but this estimate is has statistically significant results. So the common sense is that a small coefficient usually indicates a tiny effect or lack of effect, which usually indicates a relatively large p-value. So what is the reason of this weird regression results? So I found 3 possible reasons. The first reason is maybe it's due to the big data. The principle 5 in ASA statement on p-value says that any effect, no matter how tiny, can produce a small p-value if the sample size is high enough. So the big data is one possible reason. And the second possible reason is the randomness. We know that the randomness can also lead to the large disparities in p-values. The third reason is the large effect size. although the estimate of the parameter is small, the true effect size may be large. So here the effect size measures the degrees of deviation from the null hypothesis in the underlying population. So these three possible reasons. The key issue in our workshop actually is we would like to know whether the small p-value is caused by the large sample size or caused by the actual magnitude of the effect size. We don't consider about the randomness because we cannot control the randomness. So we just consider these two reasons. And the pre-mentioned p-value problem is as follows. Applying small sample statistical inference to large samples is that even tiny effects can become statistically significant. So this is the pre-mentioned p-value problem. In other words, actually, it's like the problem with big samples is that the statistical tests are more sensitive. So it's like the machine sensitivity. Very small deviations can also be detected. But in fact, such small deviations may be considered negligible or even no deviation. And actually, in practice, a very small deviation is meaningless. So that's a problem. Okay, this slide is about the some references on this issue. So due to the time limit, I just put it here. If you want to read it, you can check this list. And then we move to the power function. So there are two ways to calculate the power. One is the theoretical power, and this is suitable for the case that we already know the alternative distribution. We have this information of the alternative distribution. And this is the mathematical formula for this theoretical power. This omega here is the rejection region, and this is the conditional probability under the when the alternative hypothesis holds, then the probability that the test statistic falls into the rejection region. And but however, we usually don't know the alternative distribution. So under this case, we use the empirical power to estimate the true power. This case is suitable for cases that the alternative distribution is unknown. So it's a ratio. We repeatedly generate sample data many times, and then we do a hypothesis test each time. The numerator here is the number of times the null hypothesis is rejected. And the denominator here is the number of the rejections. So this is the empirical power. And now this is the relationship between power and the p-value. Because we previously we always talk about the p-value problem, but later we will talk about the power analysis. So what's the relationship between the power and the p-value? This is a derivation here. The left part is the power function, and then it can write to this formula. And then from this derivation here, we can see that the higher the value of our power function, the higher the probability that the p-value is p-values are less than 0.05, which means that we can easily get statistically significant results. So the previous mentioned p-value problem now turns to the high power problem. It is always easy to get a small p-value in the case of a large sample. The essential reason actually is because of the power function, the high power function. Okay, next slide. we will talk about the poor analysis for PLS. And since there is no model fit involved in PLS, we only studied the poor analysis for past coefficients in PLS. So this is a testing problem. The beta I here is the one past coefficient in the population model. And this is a testing problem, the test statistic, and we assume that under the null hypothesis, the test statistic follows the t-distribution with the degrees of freedom n minus k minus 1. And if we have this information, we can calculate the t-values, and then we can get its associated p-value. And then the poor, this is a calculation of the poor. The C alpha here is the critical value of the t-distribution, the same t-distribution. So to conduct the poor analysis, we have 3 problems to solve. The first problem is the standard error of the bit I hat is unknown. We can use the bootstrapping to solve this problem. The standard errors can be estimated with 500 bootstrapping replications. And the second problem is that the alternative hypothesis is unknown. We can specify one, so we can also solve the second problem. Then the last problem. The last problem is that the alternative distribution of the test statistic is unknown. And to solve this, we will use the Monte Carlo simulations. And next, we will show you how the Monte Carlo simulations can be used for poor analysis with PLS. And this is the reference paper. For more details, you can check this paper. Then the first step is specifying an H1 model about which we are interested in assessing poor. We need to specify all the parameters in the population model, such as the indicator, the loadings, and the residual variances, and so on. And then the step 2 is the simulation step. We draw M repeated samples from the population. So in this step, we can generate both normal and non-normal data, and the number of the Monte Carlo replications is usually larger than 500. We can also specify the sample size n. You can specify the number you are interested in to get its associated power. And the last note is that in default, we usually set the bootstrap replication number to be 500 to estimate the standard errors of the past coefficient. Then step 3. Step 3 means that in each replication, we use the generated data to calculate the p-values. So the steps are as follows. We can calculate the estimated past coefficients, and then the standard errors can be obtained via bootstrapping. And after this two, we can calculate the test statistic, and then we can get its associated p-value. And the last step is calculate the empirical pairs of the past coefficients. So here we do not know the alternative distribution, so we use the previous mentioned empirical pair. We use this formula. Actually, we use this ratio to estimate the true pair. So this slide tells us the conditions that affect the poor. So maybe we are curious about which things will affect the poor. I will say that the number of the Monte Carlo repetitions M actually will not affect the true power. As this number M increases, the empirical power will tend to the true power. And actually, the sample size N actually will affect the true power. When the sample size N increases, the true power will increase. Let's look at one example. The left part is a model. And from the tables in the right side, we can see that as the M, the replication number increases from 50 to 500. The power is similar. The empirical power are similar. Here we look at the 3 passes. The power is similar, but actually as the replication number increases, this empirical power actually will tend to the true power. And then we look at the last table. When the sample size increases from 100 to 376, the power increases to a large degree. You can say this for the first part, the power is 0.32 for the sample size 100, but for the last sample size, the power is 0.77. So we can say that the sample size really will affect the power. Then let's look at the power analysis for CBS-EM. Then first we talk about the power analysis for test of fit. Here are the reference papers and the reference book. Also, if you want to get more details, you can refer to these books and papers. And then we look at the chi-square test of fit. The null hypothesis actually represents that the specified model holds exactly in the population. And the alternative hypothesis states that one cannot find a vector of parameters gamma such that the model implied covariance matrix sigma gamma is equal to the population covariance matrix sigma 0 here. So this is the null hypothesis and the alternative hypothesis. And then to test the model fit, we use the likelihood ratio test statistics as follows. This is a test statistic, and under the null hypothesis, the test statistic follows a t-distribution, a central t-distribution with the degrees of freedom d. D is has this formula, and then once the data is given, we can calculate the observed test statistic, and then we can calculate the associated p-value here. And then under the alternative hypothesis, the test statistics follows a non-central t-distribution with a non-centrality parameter lambda here. So here, under the null, we follow the central t, and under the alternative, we follow the non-central t with a non-centrality parameter. And this is the formulas for the power. So to conduct the power analysis, we also have some problems. So the first problem is that we do not know the alternative hypothesis. So we need to specify one. And the next problem is that this non-centrality parameter lambda is unknown. So for the calculation of this lambda is a little complicated. So you can refer to this paper. This paper studies how to calculate this lambda. And then let's look at the steps. The first step is that we specify the null hypothesis. And the step 2 actually is we specify the alternative hypothesis. And the alternative model actually is the same as the original model, except that it now includes additional parameters. So that's the difference between the alternative hypothesis and the null hypothesis. And the last step is to calculate the non-centrality parameter and the power. We now move to the conditions that affect power. So similarly, we look at what things will affect the power. The power actually is a function of the non-centrality parameter lambda, the degrees of freedom d, and the significance level alpha. And here, the non-centrality parameter lambda is positively associated with the sample size n. So after we know this information, we know that keeping other parameters fixed, as this non-centrality parameter lambda increases, the true power will increase. Also, if you increase the sample size, the non-centrality parameter lambda will increase. So the power will also increase. And then if you increase the degrees of freedom, the true power will also increase. And then if you increase the significance level, the true power will increase. Then similarly, we have another example. The model actually is the same model in PLS. We studied in PLS. This is a model, and here we also look at the tables here. If we increase the sample size from 100 to 376, the lambda, the non-centrality parameter lambda increases, and then the d is the same, degrees of freedom, and then we can look at that the power is increasing. So that's a relationship between the power and the sample size and degrees of freedom. Then we move to the RMSEA test of fit. This RMSEA test actually use the same underlying statistical distribution theory for determining the power. The difference actually is that we now have the relationship between the non-centrality parameter and the RMSEA. In this formula, we can say the lambda actually is positively associated with the RMSEA. And we know that RMSEA actually is a measure of the discrepancy per degrees of freedom for the model. So here are the guidelines for the evaluation of the RMSEA. Then for this test, we also look at the conditions that affect power. So similar to the chi-square test of fit, the power is also a function of lambda, d, and alpha. The difference is that here lambda is a function of the sample size n, the degrees of freedom d, and the RMSEA. So keeping other parameters fixed, when the lambda increases, or any terms that produce a greater non-centrality parameter, such as you can increase d, you can increase n, you can increase the RMSEA, the lambda will increase, then the true power will increase. And then similarly, we have the d increase, alpha increase, the true power will increase. Let's look at the following tables. Also, if we increase the sample size from 100 to 376, we can see the power increases from 0.857 to 1. Then the last power analysis for CBSEM. Here, this time we started the power analysis for path coefficients. Also, this is the reference book. We will know how to estimate the power of the path coefficients in CBSEM. There are two methods to test the path coefficients. One is a z-test here. This is the method 1 here. However, the parameter standard error is sensitive on how the model is identified for the z-test. So we usually recommend the method 2. Method 2 here actually is using the chi-square test of difference between nested models. And here also the reference book. Then if we use the chi-square test to test the difference between path coefficients, under the null hypothesis, the test statistic follows a central chi-square distribution with degrees of freedom 1. And then under the alternative hypothesis, the test statistics follows a non-central chi-square distribution with degrees of freedom 1. And now we have a non-centrality parameter lambda here. Then the same thing, we look at the conditions that affect power. So in this time, power is a function of the non-centrality parameter lambda and alpha, because now the degrees of freedom is 1. We already know it. And then the non-centrality parameter lambda is positively associated with the sample size n. So keeping other parameters fixed, as the non-centrality parameter lambda increases, the true power will increase. And as the alpha increases, the true power will increase. The same conclusion. And the similar example, we also use this example. We look at the first parts, the PA to the SA, this the first part. And then when the sample size is 100, the power is 0.72. And when the sample size is 376, the power will nearly tend to 1. Okay. In summary, we focus on we would like to emphasize the importance of power analysis and to ensure the reliability and validity of the research results. So that's the meaning of our workshop today. So thanks, and any questions?
Okay, that's our talk here. Any questions about our topic here? As we see, not too much audience here, as I expected, because of what? The power analysis in the IS is still not popular. Because of what? Then our top journals ignored this area. But as we compare to the other discipline, especially in the marketing or psychologists, they are doing really good in the past 30 years. But in the IS, as you see, I show you the evidence in our top journals, then we are not. So that's why we try our best to help our IS community to take a look at the power analysis. And about the last few months, I also can show you the message. As I discuss these issues with the Professor Ringo, he's the developer of the Smart PLS. Then he told me he will discuss with his team to provide the power analysis in the near futures. And of course, we cannot make sure when. And I sent this issue to the editor-in-chief of the MS Quarterly, the Professor Andrew. He also recognized these issues is very important. So we still need the other editor-in-chief of the top journals to know that it's very important in our eyes field. For what? Because the statistical power is the probability their statistical test will correctly reject a null hypothesis. That's the 30 years ago, the Professor Belady and Olioski, they already told me, but we neglect this or we didn't take it into considerations. So I want to thank you, the Professor. She invited us to give these presentations. If you have any questions, you can ask us. If you need the R-code, right now, the most of the software don't provide the SEM power analysis. The power analysis, that the software that provide the R squared, the T, the Z, and so on, the static test. The SEM not too much. So if you need the R-code we present to you today, you can send me emails. I can send the R-code to you. And any questions, we really welcome your comments and the questions.
We have one question in the chat table. The Hassan asked how to calculate G-power when I want smart PLS. Oh, I mean, how can I get the required sample sizes for PLS SEM using G-power? You can answer it.
Okay. Right now, I use the G-power for many years. So there's no solution for the G-power now for the stratification model. You can only use it for approximately, like the simplified regressions way to calculate it. But if you want to get the real values, we still need to use the R code to calculate. And of course, maybe some other software we are not know. At least I know the G-power very much. So that's my response here. Any other questions? So
I think that's it. I think everyone enjoyed it very much. Thank you.
Okay, let's end here. Thank you, Professor Smith and the Professor Xu. Let's end our section here.
I have the recording too of that session, so if anyone would like it, I can email the link to them if you wanted to have the session recording. So send me an email.
Oh, please send me the email.
Okay, I'll send you the link when it comes through.
The Professor Xu, do you have any comments? We are going to end this session here.
I really appreciate your presentation, and I really enjoyed your talk. I think it's a heavy rain here. I'm not sure if my voice can come through Zoom. It's a heavy rain just behind me. Anyway, I think your talk is what you mentioned about the methodology is critically important in our field. And you have been starting to get the voice out, and I'm sure not through the only ACEs, but like PACSes, ICEs, MCs, along the way, you will get more and more attention to bring people to this attention to say, there's something we can do better, right? And I also I'm also aware of the situation in marketing because statistics or obviously quantitative research has been a traditional method in marketing. So they do it much more rigorous way, but flexible. We've been focusing a lot on theoretical side, how rigor on theory, but we do pay a lot of attention on the rigor of research methodology. But the type 2 error, as I mentioned, has been neglected in the field. I think we are catching up because of the people like you, just pushing this group through in the field. If possible, I'm not sure if you are, and put this way, and also good to know you get support from Professor Andrew Jones. That's a big plus, and to get the voice across the field, and I appreciate that, and good from me, and I really appreciate you accept our invitation and spend your time on this topic in our conference. Thank you.
Thank you. Thank you, Professor Smith and Professor Xu. Okay, let's end here. Thank you, everyone. The professor.
Bye, have a good day. The rest of the afternoon. Bye.
Bye. Have a good day.
Have a good day.
Nice to meet you, Gao Jia.
Nice to meet you, Professor Xu. Yeah.
I see you around. Thank you. 梁教授，谢谢你啊。等我回去中国见。
欢迎，拜拜。
Bye. 谢谢。Hi, Steve. Nice to see you.
Hi, how are you?
It's good. Well, better, it's record. It's still recorded.
Yeah, I'll switch it off.
Yeah, it's still recorded.
Great. Not just the 4 of us, all right? Much better off now. We're on camera. All right, I wish you a good time in China. I know it's much better in China than here.
Welcome. See you next time.
I'm waiting for the border to be opened. And I cannot afford the 4 weeks of quarantine time. I'm waiting.
Yes.
I'm waiting for the post pandemic time. Steve, sorry.
I can't switch off the recording.
You can't switch off. We've been talking.
Yeah, I know. I'll snip it off of this. It's not.
Okay. Bye for now, everybody. And nice to see you again. And thank you for the contribution to our conference. Bye.
Bye.
I've been pushing my computer too hard today, and it's locked up, and it's locked up on record.
I'm sure you've done the right thing. It's about the technology.
Bye-bye.
Bye.
Bye.